Hi, so welcome back. We are starting a new chapter today, a new unit, and the unit that we are doing is equilibrium. This will really carry over a lot into the next unit, which is on acids and bases. So a lot of what we learn here, we will use also in that chapter. So we'll look at some of the topics that we are looking at in this unit. The first is just an understanding of what equilibrium is, how it's when the rate of the forward and the reverse reactions are the same. We'll talk about how we represent equilibriums. There's something called an equilibrium constant. And we will eventually get into a lot of math surrounding this. So this picture here is just helping us sort of understand this concept of equilibrium. So in this first sample, it's a sealed gas tube, we have only N2O4 gas, dinitrogen tetraoxide, and it will just decompose and break down to two nitrogen dioxide gas molecules. But that reaction does not happen 100%. It doesn't go forward so that all of the N2O4 gets used up. What happens is, depending on the temperature, a certain amount of it will go and make products, and then the products will reform the reactants. And you can see here the different temperatures. In a really cold scenario, it's N2O4. As the temperature increases, the reaction proceeds more to the right. So at a higher temperature, we have more NO2, nitrogen dioxide. So we'll talk about how temperature relates to this and how we can mathematically represent that. This is that same reaction, the nitrogen dioxide and N2O4. You can see here, look at the starting time. So we started with all of the colorless N2O4, and over time, this would be at a specific temperature. Over time, it decomposed into NO2, and at some point, the amounts of NO2 and N2O4 sort of stopped changing. They leveled off. And that is not because the reaction stops. That's because the forward reaction happens at the rate of the reverse reaction, right? Equilibrium is when the rates are equal. And you can see that on the diagram on the right, that the rate is the the rate is the y-axis, and you can see that at first the forward reaction, which is the N2O4 decomposing, starts out really fast, and then the rate eventually slows down. The reverse reaction, which is NO2 making N2O4, that reaction starts out slow, and then, or the amount of that starts out slow, and then it gets larger and larger and larger until eventually the rate forward and the rate reversed are the same. And that's the definition of equilibrium. That's what's equal at equilibrium. So it's not equal amounts. You can see over here when amounts is the y-axis, it's not equal amounts of each, it's that the rate forward and the rate reversed are the same. 15.2 is on the equilibrium constant, and we will do almost all of this chapter is chapter 15 with a little bit of chapter 17 at the end. So the equilibrium constant is a formula. We will learn how to figure out this formula, and then there is also a way to compare equilibrium concentrations to starting concentrations. And we will learn how to calculate that either from starting concentrations or equilibrium concentrations. So here is the same, similar, I should say. This is the same. The two graphs before you are very similar to the graphs at the beginning of this chapter. It's a different chemical equation. This is the synthesis of ammonia. This is a really important chemical equation. So you can see, starting with only nitrogen and hydrogen, the nitrogen and hydrogen concentrations, that's what's on the x-axis, decreases, the concentration of the product increases, and eventually the concentrations level off. They stop changing. The concentrations stop changing when the reaction is at equilibrium, because the rate forward is equal to the rate reversed. So as soon as a molecule of NH3 gets made, a molecule of NH3 decomposes. And you can see that even if we start with only products, even if I start with only NH3, the reaction proceeds to equilibrium so that eventually there are the same proportion of hydrogen, ammonia, and nitrogen, depending whether I start with reactants or start with products. And that's what the equilibrium constant is representing. What is that ratio of reactants to products? So obviously, equilibrium is when rate forward and the rate reverse are the same. And we wrote rate laws to describe the rate and how it is related to, if it was an elementary step, how it was related to concentration and the exponents. And we're going to do the same thing here. The equilibrium constant in terms of concentration for a general reaction is equal to the concentration of the products raised to their exponents over the concentration of the reactants, again, raised to their exponents and multiplied by each other, not added. So it's sort of like the rate law for the reverse reaction over the rate law for the forward reaction. So this is pretty straightforward. Writing equilibrium constants expression. So this would be KEQ. So it's a capital K, not a lowercase k. So lowercase k was the rate constant. Uppercase K is the equilibrium constant. EQ stands for equation. We will switch out EQ for something more particular. For in this case, because we are going to be talking about concentration, it's K sub C for concentration. So it'll be the concentration, brackets mean concentration, of oxygen cubed over the concentration of ozone squared. Kc for this guy, the concentration of NaCl squared over the concentration of nitrogen monoxide squared times the concentration of chlorine. We can do the same thing here. Kc is equal to the concentration of AgNH3 2 over the concentration of Ag plus times the concentration of NH3 squared. Products over reactants, coefficients become exponents. And this table is referring back to that first reaction that we saw with the brown gas and the clear gas, right? You can see if we start with no N2O4, we just start out with NO, they reach equilibrium concentrations and you could calculate the Kc. What if I start out with just even a different amount, still 0 N2O4, but a different amount of NO2? Well, my equilibrium concentrations might be different, but the ratio is the same. And even in this one where I'm starting out with just the N2O4, again, the ratio at equilibrium, the ratios are the same. This is a constant. Now, all of these questions are going to say a specific temperature because just like the rate constant changed with temperature, equilibrium constant is going to change with temperature. The equilibrium constant in terms of pressure. Remember, it's easier for us to measure aqueous solutions in concentration, but gases, it's really hard to do concentration. It's much easier to do pressure. So we can do the same things in terms of pressure. And so you can see the lowercase p down there standing for pressure. When we do that, we can't use brackets because brackets mean concentration in terms of molarity. So we would say the partial pressure of compound D, and then put that in parentheses, raised to the D power, times the partial pressure of compound E, raised to the E power, over the partial pressure of compound A, raised to the A power times the concentration, times the partial pressure of compound B raised to the B power. So you just need to make sure that you're using the P's for pressure and the brackets for concentration.